So this video is about formal charge rules and finding the most stable structure using formal charges. So by this point, if you're watching this video, I'm hoping that you already know how to draw the Lewis structures. If you don't know, I have another video that I will tag it over here. You can find how to draw Lewis structures the easy way. I also have another video about finding formal charges. So again, this is assuming you already know how to find a formal charge. So if you don't know, again, I'm going to be tagging the other video over here too about finding formal charges. But then this particular video is more about finding the best structure once you know the formal charges. So what are the formal charge rules? So the rule number one says that the sum of all formal charges must equal to the overall charge of the molecule or ion. So if there's an overall charge, all the formal charges are going to add up to that. Also, if there's a negative formal charge, it always has to be on the most electronegative atom. And you want to minimize the charge separation. So you don't really want big charges, formal charges like +2 and -2. So you want to have most of them as much as possible equal to 0. And if you need to, then there's some -1s and +1s, but that's about it. And then at last is, as I said, try to avoid +2, -2, +3, -3. Those are big formal charges. We don't want any single atom to have a big formal charge like that. All right. So when do we use formal charge to find the best Lewis structure? So there's two scenarios when the formal charge can help. One is when we want to decide on the central atom. So sometimes, for most cases, the molecule is symmetrical, so we kind of can guess who's the central atom. But there are cases that we're confused about who the central atom is. So finding formal charge is one method for finding the best Lewis structure and deciding who's going to be the central atom. And then the second time is when we're considering when to expand the octet for the elements in the third period or after. So elements in the third period, like sulfur, phosphorus, because they're on the third period of the third row of the periodic table, they have empty d orbitals, so they can have more than 8 electrons as well. So they can be happy with the eight electrons, or they can have more than 8. So that's why finding the formal charge will help you to decide if you want to do the expanded octet or if you are happy to just leave them with having 8 electrons. Okay, so let's take a look at some examples. So for instance, we have N2O. So this is one of those cases that we're not sure about the central atom. So you might by default think that, okay, maybe oxygen is a good one to be in the center, but we can try and see that actually that's not the case. So first thing we do for Lewis structures is always count the valence electrons. And then we put the central atom O and then connect it with 2 nitrogens, or I can try to put the N in the center instead. So far we've used 4 electrons, so we still have 12 more electrons. So then we start putting electrons on the outside atoms. So we put 12 over here, or same thing in the bottom, 6 on the left, 6 on the right. So we are using all of our electrons so far. But then this is the case that we see. If you look at the top one, you're seeing that the oxygen in the center is not happy because it only has 4 electrons after bonding. So that's the time that we have to start making double bonds and triple bonds if needed. So what we do is we take one of the electrons of nitrogen out, and then we make a double bond. And then we can do the same thing on the other side, take one out, make another double bond. So this way, the number of electrons is not changed, but both nitrogens and the oxygen are satisfied with 8 electrons. Or we can have another scenario. So same idea, we had 2 single bonds, but then again, the O is not happy. So instead we can make a triple bond between them. So we can take one of the lone pairs of nitrogen out, make a double bond, still not good for the oxygen. So we take another 2 out, make a triple bond. And I can technically do the same thing for the right nitrogen as well, but because the molecule is symmetrical, I'm not going to do that because it's exactly the same thing. So I'm not going to redraw it. Now let's take a look at the bottom drawing. So same scenario, we can take a lone pair out. Actually, sorry, before getting there, let's just assign the formal charges on these. So nitrogen at the top, it's -1, +2, -1, and then same thing, 0, +2, -2. Now taking a look at the purple drawing, the bottom one, so we can do the same thing. So we can take one of the lone pairs of nitrogen out, make a double bond, and then we take a lone pair of oxygen out, make another double bond. Or I can now make triple bond and a single bond. But this time we can have 2 scenarios. So let's go back to what we had from before. So we take the lone pair of nitrogen out, double bond, another lone pair out, triple bond. So now the triple bond is between the two nitrogens. Or now I can do the same thing, but the triple bond can go between the nitrogen in the center and the oxygen on the right. So same scenario, take this out, a double bond, take another one out, a triple bond, and then now we have three distinct structures. And then let's assign the formal charges here, and then this is for the last structure. All right, so now this is the time that using formal charges, we decide to see which structure is the best. So as we said, we want to minimize the charge separations. We said we don't like +2s and -2s. We prefer every formal charge to be 0, especially because our overall charge is 0. So because of that, we can eliminate the ones with the +2s or -2s on them. So the first one is out, this one is out, and at the bottom, we have this one, the same scenario. So now we're deciding between two structures in terms of formal charge. And then one of the rules we mentioned is that we prefer the negative formal charge to be on the most electronegative element. So between nitrogen and oxygen, oxygen is more electronegative. So we prefer -1 to be on that. And based on that, this is going to be the best Lewis structure. Okay, let's take a look at another example, SCN. So this is, again, another example that it helps us to find the best Lewis structure and how to decide on the central atom, basically based on the formal charges. So same thing, we count all the total electrons in this drawing. Because the overall charge is -1, I'm adding an extra electrons when I'm counting as well. So then we have one scenario with carbon in the center, one with sulfur in the center, and one with nitrogen in the center. So we subtract 4 electrons from it. So we still have 12 more electrons. We put the lone pairs on the outside to satisfy the octet for them. So same goes here and same goes for the bottom one. So we subtract all 12 electrons. So here, again, same thing. Carbon in the center for the top drawing is not happy with octet. It only has 4 electrons. So because of that, that's the time that we start taking lone pairs out and start making double bonds or triple bonds. But then for this scenario, we can have a triple bond, as we said, and a single bond on both sides. So there's going to be 3 scenarios for this. So let's draw it again for those 3 scenarios. So for the first one, let's say we take the lone pair of sulfur out, a double bond, a lone pair of nitrogen out, another double bond. Or we can take the lone pair of nitrogen out in the second drawing, make a double bond, take another one out, make a triple bond between C and N. And at last, we want to make a triple bond between S and C. So one here, another one out, one here. Okay, so we do the same thing now for the next one. But before that, let's just assign the formal charges. So there we go. Now let's do the same thing for the second one with the sulfur in the center. So we said we have 2 more scenarios for that. Now we do the same thing. Take a lone pair of carbon out, double bond, lone pair of nitrogen out, another double bond. Or from nitrogen, we take both lone pairs out. We make a triple bond between S and N. And then same thing for carbon and sulfur. We make a triple bond between them. Again, let's assign the formal charges. Okay, and then last case with nitrogen in the center. So a double bond here, a double bond here, or a triple bond between N and C, or a triple bond between S and N. And again, assigning the formal charges. All right, so now it's time to select the best Lewis structure. So as we mentioned before, we don't want the big charges like -3s, +3s. We don't want them. So we're going to eliminate them. So this is not a good structure, not this either. This one out, this one out, this one out. So see, so far we took a lot of them out. And then we said we prefer minimized charge separation. So we prefer more zeros as much as possible. Because of that, we can take this structure out because we have already 2 other structures that they have more zeros in them. And no matter what, you're going to have something with -1 because SCN has an overall charge of -1. So no matter what, there's going to be a -1. But we said we prefer the minus to be on the most electronegative atom. So in this case, nitrogen is the winner. So this is going to be the best Lewis structure. All right, so let's take a look at another example, SO2. So this example is more for examples that have like an atom in them that they can have expanded octet. In this case, we're talking about sulfur, which belongs in the third period of the periodic table. And so we want to see if it needs to have expanded octet or not. So first, we count the total valence electrons. We draw the central atom, 2 single bonds. So we subtract 4 electrons from it. So then we put the electrons on the outside. So we use 12 electrons. So we still have 2 more. Any extra electrons goes on the central atom. So here we go. So we're done with all our electrons. But again, this is the case that we see sulfur is not happy. It's only having 6. So at least it needs to have 8 electrons. So that's when we see that this is the scenario for sulfur, what we have to do is start making double bonds or triple bonds if needed. So what I do is I take a lone pair of oxygen out, make a double bond. And then, so far, based on octet rule, sulfur is happy because it has now 8 electrons around it. Now let's, because we can have an expanded octet, it's best to find the formal charges in order to decide if this is a good structure or not. So what we do is, this is just the explanation of the fact that the sulfur is in the third row, so it can have expanded octet. So we have to take a look at that. But formal charge is what it actually helps us to decide if which scenario is the best for it. If it wants to have 8 electrons or if it wants to have more than 8 electrons. So we assign the formal charges to them. So far we have a +1 and a -1 for 2 of them, and the oxygen on the left is 0. So we said we like minimize charge separations. We like more zeros. And the fact that sulfur is in the third row and it can have expanded octet, it tells us that possibly we can have another bond connected to the sulfur, and that way we can make more zeros. So to do that, what we have to do is we can maybe take another lone pair out from this oxygen and now make another double bond. So if you count the electrons on sulfur now, it has 10 electrons, which is fine based on octet rule. It's fine because we said sulfur can have an expanded octet. So now when you assign the formal charges, you see that everything is 0. And this is actually a preferred structure compared to the previous one. So the previous one had 0, -1, and +1, whereas here we can have all zeros, and that's a better structure. Okay, and then another example, PO₄₃-. So we count the total number of electrons. Again, I added 3 electrons here because of the fact that the overall charge is 3-. So 4 single bonds, subtract 8, put 6 electrons on the outside atom. So we are using all 24 electrons. So we have no electrons left. Again, P is in the third row, so it can have expanded octet. And that is because we said in the third row, we have empty d orbitals that it helps the extra electrons to go in there. So this is possible for it. So formal charge is the best way right now to decide if P is happy with this structure or if it's better to go for an expanded octet right now. So what we do is we assign the formal charges. So now 4 things have a -1, 1 of them is +1. So the overall charge is 3-. So yeah, they all add up to 3- anyways. But the thing is, because the overall charge is 3-, we prefer 3 things to be -1 and then 2 of them to be 0. And that's only possible if we make another double bond connected to phosphorus. So what we do is we can take one of the lone pairs of one of the oxygens out and make a double bond. And then now if you assign the formal charges, you see 2 things have a 0 and we have 3-1s. And that's actually the best structure for this molecule. So what we can do is, because the molecule has a charge, overall charge, we open a bracket, we put the charge on the outside. And this way we say this is the best Lewis structure for PO₄₃-. So that was it for this video. Thanks so much for watching. If you enjoyed the video, please don't forget to like it and subscribe for more videos. Hope to see you in the next video.